Hi everybody, hope you're doing well. If you're watching this video, that means you're starting week 4 of the 4th marking period. This is still within Unit 8, Lesson 7. This lesson is going to talk you through how to solve exponential equations. This is going to continue to tie in what you've been learning all chapter with exponential and logarithmic functions. You'll see logs pop up in this lesson as well. The next lesson will continue with equation solving, but we'll focus on how to solve logarithmic equations, and that'll tie in the exponents as well. So a lot of equation solving here this week. So, quick property we're going to look at here in terms of how to solve exponential equations. And it might seem like common sense, but this will be helpful as we start to solve these type of problems. Basically, if you're trying to solve for exponents, one of the most helpful things you can try to do is get bases to equal each other. So you can see in this little box at the top, b to the x equals b to the y if and only if x equals y. Here's what that means. If I have a math problem such as b to the x equals b to the third power, those b's are the exact same base. If I have the same base, all I have to do is set the exponents equal to each other to solve for x. Now in this case, this is a really simple problem here because it's just x and 3, therefore the x value would have to be 3. The easiest type of problem with this that we're going to see are when the bases are the same. We can directly set the exponents equal to each other. The second level of that is when you have different bases, but they can be written as the same base, and we'll talk about that in a few problems here. And then the hardest version of when you can't really write the bases as the same, how do we go about solving? So we're going to look at 3 levels of problems here, 8 total examples throughout this lesson. So let's take a look here at example number 1. 2 to the x equals 2 to the negative x plus 4 power. I call this again the easiest type of problem because we have the same base. Each side of the equation has a base of 2. What that means is all I have to do is take my exponents and set them equal to each other. So to solve for x, since I have the same base, I can just go ahead, set the exponents equal to each other. X equals negative x plus 4. You know how to solve an equation like this. You've been doing this for 100 years. Let's get the x's together. So I'm going to add x to each side. 2x equals 4. Divide by 2. The x value is 2. Ultimately, I can do a quick check. So on the left side, I can plug in the 2. On the right side, I can plug in the 2. 2 squared is 4. 2 to the negative 2 plus 4, that ends up being 2 squared. 4 equals 4. And that all checks out. So not very complex math, especially when the bases are the same. If the bases are the same, set the exponents equal to each other and go solve for the x value. Number 2 is the exact type of problem. I see a base of 10 and another base of 10. All that means is I take the exponents and set them equal to each other. So all I'm going to do is solve for x. 3x minus 4 equals x plus 4. So we'll move the x over by subtraction. Move the 4 over by addition. Divide both sides by 2. X equals 4. And again, just to do a quick check of it, I can plug that back in just like we would any other equation problem. So I get 10 to the 8th on the left side and 10 to the 8th on the right side. You don't need to punch it in because 10 to the 8th will give you the same value no matter how many times you punch it in the calculator. So ultimately, if you are solving these problems, the easiest thing to do is have the base be the same. Now, you can see explicitly the bases are the same, set the exponents equal to each other. That should be pretty simple. Where it definitely gets a little bit more difficult is this next batch of examples here. So you can see it up at the top here. There's a couple bullet points I'm going to point out. If you have different bases, you've got 2 options essentially. The first option, rewrite the bases so they are the same. So what I mean by rewriting the bases, so as an example, if your bases are 4 and 8, okay, so you have 4 to the something something and 8 to the something something on the other side, I can take 4 and rewrite that as 2 squared. I can rewrite 8 and rewrite that as 2 cubed. The reason why that's important is because though I now have different exponents and we got to use some basic exponent properties mixed into this, having the same base will then allow me to ultimately just equate the exponents like we did in the first 2 problems. That is an easier way to solve these problems. If you can't rewrite the bases so that they're the same, so you get really incompatible numbers like 6 and 23, or just there's a whole bunch of combinations that it's not going to be easy to come up with a same base like you'll see in the examples we'll start off with. If that's not possible, we're going to rewrite the equation in logarithmic form. As we've gone over multiple times, the way to figure out an exponent is to write a logarithm. And as we've talked about, we'll look the other way in the next lesson. We can take a logarithm and rewrite it in exponential form. So again, knowing how to turn those problems inside out is going to be very helpful for some of these last problems that we're going to tackle. So this first bullet point, though, I'm going to use for numbers 3, 4, and 5. And you'll see why here, because the numbers here are actually pretty compatible and can be rewritten pretty easily if you know some basic facts. So, number 3. I have 9 to the 2x equals 27 to the x minus 1 power. Again, face value, I do not have the same base. So I cannot just equate the exponents to each other. Not yet. What I want to do, though, is look at that 9 and 27 and think, how can I rewrite 9 as another base to a power and do the same thing for 27? What I can do is this. 9, hopefully you'd agree, is the same as 3 squared. 27 is the same as 3 cubed. So all I'm doing, I'm keeping the original exponents the same, so those don't magically disappear by any means yet. All I'm doing is I'm taking the base and I'm writing it so that I have a common base. Okay, because now what you'll see is my base is going to turn into a 3 rather than 9 and 27. It's just that we had to rewrite it as a different power. So again, 9 can turn into 3 squared, 27 can turn into 3 cubed. Once we do that, basic exponent property, if you have exponents that are piggybacked, all you do is distribute them to each other. So if I have 3 squared to the 2x, I multiply the 2 and 2x. It becomes 3 to the 4x. If I have 3 cubed to the x minus 1, I take the 3, multiply it to the x in the negative 1. That becomes 3 to the 3x minus 3 power. It's the exact same problem as what we started with, but now we have the same base, which now will make this solvable like we saw in examples 1 and 2. So once I'm at the point where I have the same base, you take the exponents, you set them equal to each other. So 4x equals 3x minus 3. Again, we move stuff around, subtract the 3x, I get x equals negative 3. Now again, ultimately, we can check it in the problem up at the top. So I'd have 9 to the 2 times negative 3 equals 27 to the negative 3 minus 1. So that gets me 9 to the negative 6 equals 27 to the negative 4th. And again, you can use your calculator to equal all those things out. Again, you'll get some really low fractions, but ultimately you will end up with the same answer. So again, you can still plug it back in and check. If it's a little bit easier, maybe plug it in a couple steps above here where you have the same base so you can clearly see that they equally match up. But ultimately, use your calculator to check your math. Number 4 is the exact same idea. Now, what I would maybe suggest here is hit pause for a second and think. We know 125 and 5 aren't the same. How can I rewrite it so both those numbers are the same base? Let's talk about this. So 125, I can rewrite that as 5 cubed. Now, the fact that I make that a 5, if I look at the other base here that's already a 5, I don't need to do anything to it. I already have the same base. You could theoretically rewrite it as 5 to the first, but it ends up coming out to the same thing anyway. So sometimes you can look out and get a problem like this where only one of the bases has to be rewritten so that you can get them to match. But ultimately, I can turn 125 into 5 to the third. And again, what that'll do for us is give us common bases. It'll give us a base of 5 on each side. So again, I'm going to use the same exponent property. 3 and x are going to get distributed. So on the left, I'm going to have 5 to the 3x equals 5 to the 2x plus 5. Now that I have the same base, take the exponents, set them equal to each other. 3x equals 2x plus 5. Subtract the 2x, I get x equals 5. Now, for the last one here, You can do the same thing, but what I'm sure you're looking at is, oh, that's a fraction. Why are you doing this to me? This is certainly still doable. I'm not saying you have to really worry too much about this, but this is definitely one that can be rewritten as the same base. So let's talk this out here for a second. So I have a base of 4 and a base of 1/2. I can rewrite 4 as 2 squared. I'll write that a little bit neater here. And then we still have that power of the x on the outside. Now, if you're thinking, well, what do I do with 1/2? Well, because it turned into a fraction, think about this. How do we turn a base into a fraction? Negative exponent, everybody's favorite thing. So we go ahead and we can rewrite 1/2, 2 to the negative first. Again, if you do some quick mental exponential math, 2 to the negative first is the same thing as 1 over 2 to the first, aka 1/2. So that's how I can rewrite that base, taking that to the power of x minus 3. So again, I can get a common base here of 2 by putting a little bit of thought into it. Again, I know that's a little bit more difficult because, again, now we're flipping from fractions to integers, but ultimately, negative exponents will allow you to flip things around. So, follow me from here. That's the hard part. Now it gets easier. Let's go ahead and rewrite this with our exponents combined. So I'd have 2 to the 2x on the left. On the right side, I'd have 2 to the negative x plus 3. And again, common base. We go ahead and set our exponents equal to each other. So 2x equals negative x plus 3. Add x to each side, I get 3x equals 3. And do some quick division here, I get x equals 1 as a final answer. So, those first 3 examples up at the top. Again, you have bases on both sides. They were, I'd say easily, relatively, if you want to use that word. But you can rewrite them as the same base. Now, ultimately, if I give you problems, more than likely they'll be like 3 and 4. And I'm not going to have you have to do some crazy math here to figure out what bases things should be. We're not going to try to do like bases of like 21 to the 4th or 19 to the 7th or anything big like that. But, your 3 squareds, your 5 cubes, your 4 cubes, those types, hopefully those are numbers you've seen enough times where you can semi-quickly come up with those. Okay? So that's one way. Now the second way is if you can't rewrite the bases so that they're the same. So if you look at 6, 7, and 8, now we'll talk more about 7 and 8 in a second because they've got a couple of extra little algebra steps in the way. But let's look at 6. I have 4 to the x equals 11. So on one side I have a 4 as a base. The other side, I know there's not an exponent there, but technically 11 is still a base. It's just 11 to the first power. You can sit all day. It's going to be really, really, really complicated for you to figure out how to get a common base for 4 and 11. So we're not even going to try with that. What we're going to do instead is we are going to rewrite this as a logarithm, okay? So since there's no real easy common base to get to, rewrite this in log form. So remember, when we rewrite this in log form, the base that you're starting with here, so the base of 4, that's the base of the log function. It is equal to the exponent. So it's going to be equal to x, and then the number here that's at the end, that's what goes right next to the log base 4. Now you'll notice when we rewrite this in logarithmic form, it's pretty much set up for us. Log base 4 of 11 equals x. All we really have to do now is enter this in the calculator. So, as a quick review, to enter this in the calculator, remember, we do that change of base formula, and I went through that in a previous video a couple of sections ago. But the way that you always do it, notice how I have log 11 over log 4. The base is always on the bottom of this fraction every single time. So as long as you put it in this order, you'll get the correct answer. So you'll get, again, some pretty gross decimal for x. Again, round just for accuracy's sake, we're going to go to 3 places here. 1.730 is what this would round to. Now again, since you're getting these gross decimal answers, you may not be so sure if they're right. Go back to the original problem and plug it in. So if you go 4 to the 1.730 power, Now again, since you're rounding, it might not be a perfectly exact answer, but it should be pretty darn close. It might give you like 11.01, something really close. If it does, then that means you did your math correctly. If not, check the way that you rewrote your exponential to a logarithmic expression. Make sure you punch things in the correct order, etc. But ultimately, I would definitely plug these back in real quick, check to see that you got the right x value. Now, 7 and 8, pretty much the same idea. Now, the thing about 7, we have 3e to the 2x equals 36. Now, when you do these, what I would suggest is to get that exponent term by itself. And what I mean is, you've got this extra 3 hanging out in front of e to the 2x. I would divide that away, just like you would any other algebra problem. So if you have something that's being added, subtracted, multiplied, divided, get that out of the way first, just like you would any other algebra problem. So I'll divide both sides by 3. I'll get e to the 2x equals 12. So if I look left and right, I've got a base of e, I've got a base of 12. There's no way on earth you're going to get a common base out of those two bases. So we have to write this in logarithmic form. Now, keep in mind, you could technically do this one of two ways here. E deals with natural log. So, you could technically write this as the natural log of 12 equals, remember, it's always equal to the exponent, so that's why I'm going to this order, equals 2x. There's a button on your calculator that says ln, it's running in a log, so what you can do is you can type that in, you can divide away the 2, that's ultimately up to you. What will happen is that'll give you an x value of roughly 1.243. That's one way you can do it. Or you can still write this in logarithmic form and it will work out the same way. So again, your base is e. You could say log base e of 12 equals 2x. And again, you could do your change of base formula, log 12 over log e equals 2x. So again, if you decide to do it this way, so this is a longer way to do it, and again, that's why it's helpful to know that e is natural log, because it does shortcut your math a little bit here. But if you do this, you will end up with 2.485 equals 2x. Divide by 2. And you'll get something around 1.243. So you get the same answer either way. If it's more helpful for you to just keep things as everything's a log, 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 that's fine. But e does represent natural log, and that's the way you can convert that back and forth. So either way, I don't really care. Whichever makes more sense to you, be my guest to use. All right, last one here, number 8. Same idea. So it's another equation. We have this extra -6 that's in the way. Let's move it. Again, if you see any basic operations, get them out of the way. So we can rewrite this as 8 to the 3x equals 11. And again, same deal. There's no common base for 8 and 11. Don't bother trying. Rewrite this in logarithmic form. Log base 8 of 11 is equal to the exponent 3x. And again, as I said in the other two problems, the log expression, when you rewrite it, has to be equal to the exponent every single time. So, again, using our change of base formula, log 11 over log 8 equals 3x. So when we do that, we get approximately 1.153. Divide that by 3, and you get a final answer for x of approximately 0.384. So again, for accuracy's sake, especially with these log expressions that go on forever, try to remember to go to 3 decimal places because it will make your final answers more accurate. But ultimately, this is how you solve exponential equations. So, like I said in the beginning, there's definitely layers of easiness and difficulty to them depending on what's given. So again, I would definitely suggest you've got those extra homework, quote unquote homework practice problems. Maybe do a couple of those before you dive into the graded assignment. If you get to the graded assignment and you're still confused on what you're doing, as always, send me a message on Schoology, shoot me an email, or stop by my office hours on Zoom. I'll be more than happy to talk this out. I know this is probably a little bit more complicated than some of the other stuff you've been doing, but if you need the extra help, please don't be afraid to reach out. So as always, thanks for watching. Stay safe, stay healthy, and we'll see you next time.